Hi guys, there is new technique that now everybody try to implement to their inference engine like vLLM and llama.cpp, and it allows us to get 3 times higher speed of inference without losing the quality with really minimal costs. And if you look here, this is the article, and as we can see, it delivers 3 times speed up without any degradation in the output quality or reasoning logic. And we see the benchmarks on multiple of hardware because it's hardware dependent, and how it looks like, just like this. Here we can see that we run the comparison from the Google. This is without MTP and with MTP. And as we can see, we allow up to 2.11 times increase in the speed. So we'll test all of this. So who am I? I am Łukasz. I'm lead engineer that specializes on inference. And today we'll walk through to fully understand MTP, how it works with visualizations and explanations. And then we will actually deploy MTP on vLLM and llama.cpp for Qwen 3.6, 27 billion, and Gemma for 31 billion. And we'll see how much of the increase in speed we can get. Let's dive into the explanation. Another important point is that for the companies, the training is the cost, because while doing the training, they don't generate any revenue and so on. But during the inference, when they serve users, that's when actually they generate the money. Why? Because if you lower the cost by 2, 3, 4 times, then and basically means that you can serve more users that pay you the same and so on. That's why now recently you can see that all the subscriptions increase because the models were subsidized by Microsoft and others, so the compute was very cheap for the companies, but because the compute now increase, they have the same inference method, so they try to increase the prices to compensate for it. So inference is the most important part because that's when you actually print money, not burn money like in a training. Now, to understand why MTP is such a big deal, you first need to understand how large language models generate text, and I mean really understand it. So there are 2 phases every time a model generates a response: Prefill phase and decode phase. So the prefill phase, as we see, here we have a simple prompt: how to make. These are input tokens. In real models, tokens are not always full words. Sometimes one word is one token, sometimes it is split into pieces, and sometimes punctuation or spaces become separate tokens. But conceptually, we can think of them as chunk of text. This is where you hand the model your input, your system prompt, your message, the full context. The model processes all of those tokens simultaneously in parallel through its layers. It's doing a massive matrix multiplication of the full input at once. And this phase is fast because GPUs are designed for parallel computation. You are throwing a huge chunk of work at the GPU and it eats it up. And the result of it is the first token that will be the output token. So in this case, it's the inference. And the moment when we get the first output token, the generation becomes fundamentally different and fundamentally slow, because the model generates one token at a time, not one word, not one sentence, one token, which is roughly half of a word on average, like this. So we have faster, with, and so on. Each new token requires a full forward pass through entire model. So if we get inference, it uses this. Then if we get faster, it uses all of this. And then for width, we need all of this, and we need to do forward pass through entire model. You pass the previous output back in, you run it through all layers, get new token, pass that back, run it through the layers again. This is why decode is sequential. Token 1 depends on the prompt, token 2 depends on the prompt plus token 1, and token 3 depends on the prompt plus token 1 plus 2, and so on. That dependency chain is the core reason autoregressive generation is hard to parallelize. Let's say that dependency chain is the core reason autoregressive generation is hard to parallelize. Let's say your prompt is how to make inference faster with, those tokens all get processed at the same time. And now there is another thing. So yeah, that's the output tokens. And then when we run it, we put this in cage. Then when we generate new token, all of this get also in cage. And then when we get, for example, faster, and we just try to generate width, all of this will be also in cage. And this is named KV vectors. And KV stands for key value. Inside the transformer, attention uses keys, queries, and values to decide which previous tokens matter for the current token. Without caching, every decode step would have to recompute attention information for the entire previous context again and again. That would be extremely wasteful. So models store the key and value vectors from previous tokens in a KV cache. Then when generating the next token, the model can reuse that cached information instead of recomputing everything from scratch. This is one of the most important optimizations in LLM serving. But the KV cache also consumes memory because longer context means more KV cache. More layers mean more KV cache. More concurrent users means more KV cache. So inference is not only about compute, it's also about memory bandwidth and memory pressure. This matters because standard decoding often becomes memory bandwidth bound. The processor spends a lot of time moving model weights and cache data around just to generate one token. So even if your GPU has a lot of compute available, the decode loop may not fully use it. This is part of why speculative decoding is attractive. It tries to use the available compute more efficiently by doing more useful work per expensive target model pass. And when we measure inference, we often care about metrics like token per second, time to first token, inter-token latency, true output, P50 latency, P95 latency, and memory usage. Because for users, this becomes difference between an AI assistant that feels instant and one that feels painfully slow. A model that produces tokens slowly feels less intelligent even if the final answer is good. So inference optimization is not only about saving money, it's also about product quality. Faster inference means smoother chat, faster agents, better local AI, better on-device experience, and lower serving cost. So now, do you see the problem here? Here is it visualized. Each clock tick, it's one forward pass and one token. So if we look, the T1 produce the first token, T2 produce second, and so on. And each obvious token pay the same full model cost because it needs everything behind to compute the next one. And here is the frustrating part. Even when the next word is obvious, the model still has to run another target model decode step. This cost is not perfectly identical for every token because the KVK changes the computation and the context grows over time, but the waste is still real. One expensive decoding step usually gives us only one new token, and it doesn't matter that the next token is completely obvious, like the model just said action speaks and the reasonable computation is louder. The model still runs a full forward pass through all of its billions of parameters just to figure that out. It's like hiring a world-class chef to microwave a frozen pizza. The skill is there, but it's complete overkill and so on. And technically, why this is slow? Because the decoding phase is memory bandwidth bound. The GPU isn't spending time doing arithmetics, matrix multiplication. It's spending most of its time just loading the model weights from VRAM to the compute cores, loading billions of parameters just to do a small amount of math, then loading them again and again. The GPU compute units are sitting largely idle waiting for the data. And this is the fundamental bottleneck, and it's the exact bottleneck that speculative decoding and MTP are engineered to attack. So here is the key idea is simple. A small draft model guesses ahead. The main model verifies the guesses in one pass. So this is the main model, the target model. This is what you usually serve. And in addition, you have a small draft model. Instead of asking a large model to generate every token one by one, we let a smaller, faster model prepare a few likely next tokens first. So now if we look at the draft model, we have the example that we have a action speak and then we generate 4 suggestions of tokens that could come after it. The target model then verify it in parallel because it do just forward pass. So it verifies that this accept these tokens, this is bad. So then this is ignored because we know that we don't need it anymore. And why we don't need it anymore? It's because when we accept the tokens, we know that last one was bad. And because we are in the decode phase of the target model, the big model, then we can generate the correct one. So we kept the valid prefix and continue and replaced it. So the key idea is the draft model proposes, the target model decides, and then speed up comes from accepting multiple tokens. Now we'll look at the example of Gemma 4 and the draft model with speculative decoding. So the diagram zoom in on the draft model itself. The drafter have the same general transformer style component as the main model, which are these. An embedding layer here, the decoding layer, RMS norm, LLM head. But it's much smaller. For the E2B, E4B, the drafter has only 76 million parameters and 4 decode layers, as we can see here. This is 4, and compared to the billions parameters in the target model. And the draft model starts with the current context, so action speak, and predicts the next token louder. Then it gets fed again back to itself and predicts done. And then it repeats the process again. And then we have the action speak louder than pens. So the draft model is still autoregressive. It still generates one token at a time. The important difference is that this draft model is a tiny compared to the target model, so those guesses are much cheaper to produce. After the model creates block of guesses tokens, the target model verifies this here. So it verifies it in this step that we saw. In parallel, actually, it goes here and then it gets accepted. So this is what goes after this. And this is what we are looking at here. So if the draft is good, the target model accepts several tokens and generation move forward quickly. If there is a mismatch, it accepts tokens up to the first wrong one, replaces the wrong one, and continues. So speculative decoding works best when the drafter has two properties. It must be cheap, so drafting doesn't not add much cost, and it must be accurate enough so the target model accepts many of its guesses. This is exactly why Gemma uses a small optimized drafter here. Now, let me be fair here. Speculative decoding is powerful, but it's not magic. Let me give you the real trade-offs. As we can see now in the advantages, we achieve the higher true output, so multiple accepted tokens can move generation forward in one verification step, parallel in single forward pass. We have also lower latency because good draft guesses reduce the number of expensive target model decoding cycles. And then quality stays controlled because the target model still verifies tokens before they are accepted, so we don't lose the quality. Then best on predictable text. So common phrases, boilerplate, and easy continuations can be generated faster, yeah, because it's easier to predict them. But there are also disadvantages. We need two model serving, so classic speculative decoding requires both a target model and a draft model. We have more memory pressure because the extra drafter model adds footprint and can complicate capacity planning and the full application. We have tuning overhead because you need a draft model that matches the target model well enough. And if we have low acceptance rate, then we generate a lot of tokens that are bad. So basically, we are adding overheads because poor draft guesses mean fewer accepted tokens and smaller speedups. So the takeaway is that speculative decoding can be much faster, but only when the draft model is cheap and accurate enough. Okay, so now we understand speculative decoding, but what is multi-token prediction specifically and how it's different? So standard next token prediction, MTP, is what every transformer does by default, and we explained it before. So this is the reminder if you want to check. So we do one forward pass, one new token, the generation advance by one position. Then MTP is here, and what it do is it keep the same speculative decoding idea, but it integrates the drafting behavior directly into the architecture rather than bolting on a completely separate model. And as we can see, we have the candidate feature tokens. Here's the key idea. The main model does its regular forward pass and produce hidden states. The MTP head, which is a lightweight model attached to the main model, take those hidden states and run additional autoregressive passes to predict tokens at future position. And the target pass still verifies what gets accepted. So this reduces repeated work because when candidates match, generation can move forward faster. But why this matter as a distinction? When speculative decoding uses a completely separate draft model, the drafter has to start from scratch, build its own understanding of the context, build its own KV-cage, work without any knowledge of what's the big model computed. With MTP, the drafter is part of the same system. It gets to use the big model's internal state, and that's where Gemma 4 engineering get interesting. So next we'll look at the architecture again. So as we can see, this is the reminder from Gemma article. So we have the actions and the target model. We generate the first token. Then we generate 4 candidates with a draft model autoregressively. We verify this token, and in this case we pick this, and then this we discard, and then draft tokens get here. So this is the example how it looks on text. So action speak louder than pens, and then because pens doesn't make sense, we delete it, and we get the words generated by the target model. And this is the example with architecture that we have before. So the target model, the draft model, and as we can see, we again have the same example. And then if we go here, this is validated, this is ignored, and then the target model generate words. Now we look at training loss, which help with scaling the MTP objective. And we can see the total loss here. When you train a model with MTP capability, you are actually training two objectives simultaneously. The main next token prediction loss is here, and auxiliary MTP loss that encourages the model to predict further ahead, which we have the MTP loss here. And then we add the 0.1 coefficient. This coefficient is to keep the MTP objective small. This is intentional because we don't want model to sacrifice its core next token prediction ability just to get good at predicting 3 tokens ahead. The main tasks stay dominant. The MTP behavior is auxiliary skill that the model learns on the side. This is the training foundation that makes the inference speed up possible. And here we have the visualization. So we want to keep this objective high and this like a secondary one, because we don't want to dominate the main task of the model. Now this part we already kind of explained, but it's better visualization. So again, what exactly happens on the rejection? We have the draft model, it predicts these tokens, we decide which tokens we take. This is wrong, so we discard all of this. Then we choose token from its forward pass. So this is the target model. And then we input this token here from the target model. And this process, this is the reminder how it looks before with the full sentence and so on. So as a final result, we have action speaks louder than words, and we have 2 tokens from the draft model and then 1 token from the target model. And this all get added here. And then the loop continues. The draft model starts again from the new context and the full cycle repeat. This is the engine running every time you use Gemma 4 model with MTP enabled. And now if we look at the specific example of Gemma 4 model, we can see that there are 3 possible enhancements of the MTP. So we have the target activations, the KV cage sharing, and the efficient embedder. And now let's look at each one by one. So the target activations, the drafter uses the target model final hidden state and combine it with token embeddings. So the drafter gets access to information the target model already computed. But we'll look into more specific example later, yeah? Because I know that it could be not understandable on the first try. And then the KV cage sharing, that makes actually more sense when you explain it, because instead of building a completely separate full KV cage, because if we have 2 separate models, then each of them will have like their own KV cage. So it's like you're doubling the memory of full conversation. But in MTP case, the drafter model can use the targets model KV cage in Gemma 4, and this saves work and memory. Then we have the efficient embedder. This apply to the edge models, so E2B and E4B. So for the Gemma 4, instead of scoring every token in the vocabulary directly, the model first narrows the search using likely token clusters. Then it computes final tokens, logits only with those likely groups. And this matters because the vocabulary can be very huge, because the context of these models are quite huge. And scoring every possible token can be expensive, especially for small drafter when the LLM head can become the bottleneck. So the summary is Gemma 4 drafters are small, but they borrow information from the target model, so guesses are faster and better. And remember, the drafter is doing all of this work with, like on the example, 76 million parameters, so it's tiny, but it punches way above its weight because of these 3 enchantments. And now we'll look at the target activations. So to make you understand the concept of target activations in Gemma 4, we will need to explain the RMS norm first. So this is a normalization step. It keeps the scale of the numbers stable before they move into the next part of the model. You can describe it as cleaning up or stabilizing the vector, but not as choosing the token. And these are activations from A to B model. Yeah. Then we can explain the LLM head. So the LLM head takes the final hidden state, and hidden state is this value, and turns it into score over possible next tokens. In plain language, we can say decides which token is most likely next. And in the diagram, the target model process the speak, and later the drafter model LLM heads will produce the louder token and so on. And the hidden state, this is the model's internal summary of the current context. So it's a vector with this 1536 numbers, and the LLM head reads that vector and turns it into a prediction for the next token. Yeah. And then we have also token embedding layer. This turns a token like speak or louder into a vector of numbers, because this model cannot directly work with words, so it needs to convert token IDs into the embeddings. So now to explain this diagram, we have the situation that target model just finished its forward pass. This is exactly what we are talking about. And it produced the token speak. And in doing so, its last layer produced the hidden state that we explained. So the vector of 1536 values that encodes the model's rich high-dimensional understanding of everything it has processed. So it's a very big number. It's a long list that represents the understanding. And normally this vector will be like just thrown into the bin, the trash, and thrown away. But not in this case. These 1536 activations are fed directly into the draft model, which is here. And the draft model also has its own token embeddings, and this is also 1536 values. So these two vectors are then concatenated together, giving us 3072 values. But it's a big vector for a tiny model, so we want something smaller. So we get it projected down to 256 values. And that's the drafter internal dimension. And this is learned compression that preserves the most important information that we want to pass. Now, think about what it means. The draft model knows not just what was the last token, it knows what the target model was thinking when it produced that token. It has context about the full process state of the larger model compressed and injected right at the start. And this is all just in round one. Yeah. And this is multiplied by 4 because we are predicting 4 tokens into the future. Yeah. So like in our example, we predicted the 4 and the pen was wrong, and then we deleted period and so on. That's why there's 4 here. So now in round 2, the draft model has generated its first token, louder, and it needs to generate the next one. Now the activation it uses are its own activations from round 1. The one that we get here, projected up because we need it in the higher scale to feed it again through the token embedding. So it's projected up to 1536 values to match the embedding stable dimension. And we do basically then the same operation, and we get projected down to 256 values and so on and so on. Then we have round 3, and then round 3 uses round 2 activations and so on. So the draft model is essentially a building chain, each round using the previous round's hidden state as a signal about where the sequence is going. This dramatically improves the quality of the draft tokens compared to a drafter that starts blindly. Now, quickly, let's look at KV cage, which we explained at the beginning, but to remind, when a transformer processes tokens, every attention layer computes key and value vectors pair for each token in a sequence, and in autoregressive generation, you need all the past keys and values to compute attention for the current token. So rather than recomputing all of these every time, we cage them, so we save them. And that's the KV cage. Now, if we look into this picture, we see the KV cage sharing. So for the Gemma 4, we have the local attention layers, which are only attended to nearby window of tokens, and global attention layers, which attend to the full sequence. And the last layer of every Gemma 4 model is always global. So this is global because its last layer, these are local, yeah? And now in classic speculative decoding, the drafter model would need to build its own KV cage from scratch, yeah, because we have it separated as two different models. But that means reprocessing the entire prompt, all the past tokens through the draft model attention layer will take time and memory. So the Gemma 4 don't do that. For the local attention layer, the draft model simply reuses the target model most recently computed local KV cage through cross attention directly to the target's cache. And this is visualized here. We have these green arrows that go to local to the decoder, 1, 2, and 3. Now for the global attention layer, since the last layer of any Gemma 4 model is always global, the draft model reuses the target's model global KV cache as well. And we can see it here as the purple arrow going through decoder global to the decoder 4 in the draft model. So why does it work? Because the draft model has a similar architecture to the target. The attention patterns are comparable, and the target has already done all the hard work of computing context representation for every token in the sequence. So why redo it? The result will be that the draft model start drafting immediately with full contextual knowledge from the target's model attention, without spending any time or memory building its own KV cache, because then we will be like doubling it. So less memory, less latency, less memory, less latency, and better drafts. So finally, there is an efficient embedder. Efficient embedder reduces the compute needed by the draft model language model head or LM head that we have here and explain. So normally after the decoder produces a hidden state, the LM head converts the hidden state into logits, which are raw scores for every possible next token. And to do that, these are the logits. To do that, it multiplies the hidden state, which is here, by a very large vocabulary matrix. And for Gemma 4, the vocabulary has 200,060 to 144 tokens. So this means scoring a huge number of possible tokens at every draft step. So for large language model, this might be only a small part of the total compute, but for a small draft model, the LLM head can become a meaningful bottleneck. Yeah, we have it here. That would be pretty expensive. So the question is, do we really need to score every single token every time? And no, the efficient embedder avoid this by using so instead of first computing logits, so these ones, for all tokens, the draft model first multiply the hidden state by this much smaller cluster table that we have here. And that gives us the cluster logits, which tell us which cluster are most likely to contain the next token. And here we have representation how these clusters can look like. Yeah, E1 is here, E2, and E3. Then only the most likely cluster are selected. After that, the model computes token level logits only for the tokens inside those clusters. So these are the cluster logits. So instead of scoring all 262,104 tokens immediately, the model first narrows the search space, then scores only the relevant token candidates, and by result we only multiply by 256, and then amount of tokens in selected clusters, and then we get token logits, and then we get the word. So to keep the token prediction quality very similar, we'll be making the drafter faster. This is the optimization that is used in E2B and E4B model, where LM head compute matters more proportionally. Okay, so now let's look at the serving methods. So there could be multiple ones, but I choose the two most popular ones, vLLM and llama.cpp. And basically vLLM is production serving engine, so it allows you high throughput with high concurrency, parallelism, and so on, and stable API deployment. The good thing to mention is that the MTP support was much faster than llama.cpp, but llama.cpp is very important because it's for local and edge runtime. It allows mainly focus on GGUF format, but also some others recently, and it leveraged the GPU and also CPU. It starts very quickly, so it's nice to use for like your local setup, like server, or if you want to chat to model at home locally without people listening. This is more for GPU reach, and this is more for like local deployment and so on, and the support got recently added to with MTP. And now we'll jump to some demos to see if it actually works and how much gains we could get. Okay guys, so now we'll quickly come to my hardware. So as you can see, AMD Ryzen 99500X. Yeah, we have 96 gigabytes of VRAM on NVIDIA RTX 6000 Pro Blackwell. We use Linux. We have 92 gigabytes of RAM and CUDA 13.1, and then 590 4801 are the drivers. Okay, now to just quickly show you, I prepared the project YAML file. So if you have UV, you can just do UV sync, and then you should have created the virtual environment with following packages that you need to use to run the test yourself. But if you don't want it, you don't need to use it, basically. Here we have the MTP version, and as we can see, we use server CUDA 13, and it have MTP supported because I checked it in the flags. We set the context to 3000, turn flash attention, 1 parallel throat, and right now I'm checking the draft nmax to 4, and the only difference with no MTP is that this is commented. And now if we look, this is the app test that I'm running, and it's currently executing the Docker that I showed you. So as we can see on the right side, we have the no MTP one, and I set the number of tokens to 1500 because this Qwen model tends to overthink, and then it takes really long to finish these tests. And I ran 10 runs because of increased token. And as we can see, the MTP version is right now 2.64 times faster. So yeah, context was before set higher, but I lowered it, so this I need to correct. And this is the prompt, the standard one, and I added to don't include emojis because Qwen like to put a lot of emojis here and so on. And as we can see, we have this running over 100 tokens, and we can see that 1500 tokens was done in 34 seconds without MTP, and this was done in 13, so we have 265 increase. And now I run the other parameters, so I'll change the n value. Okay, so I ran already one MTP, as we can see here, with the number of drafts up to 3. And as we can see, this is the average that I get from the runs, and this is the current one because I'm running now the default model. So as we can see, the increase is like around 4 times actually, which is kind of insane for the Gemma using vLLM. So I will run it maybe with 5 and 4 too, to see if we get better values there, and then I will come back to you guys later. So now we are running the MTP5, and as we can see, it looks like it will be even faster than the last one. So get around 130 tokens, so it's super fast. Okay, so now we are running the Qwen 3.6 27 billion with FP8 quantization, and we run it using vLLM. And as we can see, the results are similar to Gemma with MTP. This is for 5 version of MTP drafts. But we can see that Qwen generates much more tokens. If you watch my other videos when we test the Qwen and Gemma 4 for vision, then you know that Qwen have tendency to overthinking. Hey guys, so I'm back with the summary of llama.cpp versus vLLM multiple token prediction with speed comparison. And as we can see, the vLLM win with the Gemma 4 model with prediction of 5 speculative tokens, and we get 132 compared to baseline, which was 39 tokens. And this is because the baseline was low, because if you look then on the Qwen without MTP, we get 49 tokens on my hardware on average. So that's like 10 tokens more. So then we achieved the total speed lower than Gemma with the same number of speculative tokens predicted. So it's 259. And for the llama.cpp, I use the Q8 quant, which is similar size as FP8, but of course vLLM takes more memory. I try to capture it because with MTP it should also take a bit of more memory because we use the draft model. Yeah, but actually when I try to check it with NVTop, the value oscillates for both, and I couldn't find definitive difference. And for llama.cpp, yeah, I forget about to do it, so it is what it is. But as we can see, the baseline here was 47, here was a bit faster, and yeah, but it still used less memory, so this few tokens difference could be not that viable. And as we can see for nmax 3, it achieved actually best performance, and here it was for 5, so there is probably differences in the MTP implementation. And then here we have baseline, yeah, so for llama.cpp 47 and then 180, so it's more visual, 49, 127, and here the biggest 39 and 132. And this is llama.cpp with nmax parameter, so we can see how it changed. So as we can see, around 3 it was biggest, and then 4 and 5 oscillate, and then we have also this nmax tokens. So yeah, that will be it. So I wish you liked the video, and if you like the video, you can check my other videos when we check the vLLM or we check the visual AI with Gemma 4 and Qwen 3.6 and 3.5. So I compared all of these visual capabilities of the models for image video. And actually the one finding that we saw last time is that as we checked in the visual comparison, the Qwen still tends to, even in text, produce a lot of tokens. So it produces much more tokens than the Gemma model. And as always, this will be also in README, so you can easily check it, and the summary. And I will attach the results from both of the files as CSV, so you can also check it for individual ones. And the Docker, I also created one for Qwen 3.6 with 27 billion. Actually, here it is with vLLM. So you can also run it, and you can change parameters. Yeah, you can change the number of speculative tokens. And yeah, you can turn prefix caching, yeah, because I turned it off for the tests and so on. And also remember that if you want to run it, you need to pull the newest images. So you need to delete like your old one. That it could be, for example, yeah, here. Yeah, you can see that I use the one that is from 8 days ago. So actually here you can see the version if you want to check the exact one that I use. Here I use this I actually don't use because it's the latest and it don't support MTP. And here I use really new one for the Qwen 13 on llama.cpp. So this is this version. So yeah, see you guys in the next one.